In this lecture, we will learn a rigid body subjected with distributed forces or distributed loading. Before we solve this problem, let us discuss one more small problem where a system of forces or the bodies connected together and system of forces are acting on a particular body. If that bodies together are having more than 3 reaction forces or more than 3 unknowns to be solved, how to solve that rigid body problem? Let us, I'm not going to solve the problem, I'm going to just give you the free body diagram and then you can use the equilibrium equations to solve that problem. Say for example, we have a beam fixed here, and the beam is fixed at this end, then it will have 3 reactions, okay? Then it is also supported with another roller. Say assume it is like this and it is hinged here. It is a hinge, it's a roller, and some external forces, even here some external forces are acting. Okay. Now in this support we will have x, y, say if it is A, then AY, AX, and one moment. So 3 unknowns are there, and you have another unknown here because of this roller. So here we have the roller support, so that will exert a force like this. Now as a whole, if you see this rigid body or this as a single rigid body, then we will have 4 unknowns which we cannot solve using equilibrium equations for a planar problem. So what we have to do, we have to consider this as a separate body and beam as separate body. If I am isolating this first and this second, and then I will be able to solve this problem. So my free body diagram will be like this. It is hinged, so it will have say if it is d, dy, dx, some external force, and the roller, effect of this roller, okay, on the beam is like this, okay, and the effect of this beam on the roller will be Newton's third law. So magnitude will be equal and opposite to each other. Say if it is B and this will be B. Now I am considering this as some force is acting, this as a rigid body. So we will use all the 3 equations for this and find out B, substitute that B here, okay. Now this body will have only these 3 unknowns. So this is now known because we have separated this body and solved it separately. Okay, this is how when more bodies are connected together and behaving as a single body. Okay, I hope you have understood this. Now let us solve this problem. Now you see here, so far whatever problems we have taken, we have considered or we have solved, the forces are not distributed. The external forces are concentrated at a particular point. In this problem we have distributed forces. So you see here it is distributed and it is uniformly distributed. So at this point there is no load, and as it moves linearly it is varying, okay, and at this end it is 25 kilonewton per span. Span means this length. Okay, it is spread across this length. Okay, so now how to deal with the distributed force? Say, what is a distributed force or distributed load? Say you see wind force. So wind pressure acting on any surface is considered as a distributed load. Say for example, you take this board. Board is a surface. The wind force is acting on this board. Then that wind pressure is the distributed load. Water in a tank is a distributed pressure force. Okay, and you see sand distributed in its place in a particular floor. Okay, of a storage place. The sand spread across. So whatever is spread across the surface, if it is giving some pressure, then that is the distributed load. Okay, so pressure at each point indicates the intensity of the distributed load. Before we solve this problem, let us understand how this distributed forces are changed into concentrated load. Okay, so the distributed force or load has to be changed into concentrated load. Assume a beam having width, and you draw, so this is x direction, and draw some pressure. This is the pressure. Okay, and the force is distributed. So distributed, okay, across its length, through the length. Okay, it is distributed. So it is distributed. Okay, the pressure is a function of only x. So at any point the pressure is equal to function of x. What is the pressure? Pressure is, the unit for pressure is Pascal or Newton per meter square. Okay, so now the width B is there, right? Now how to change this into a coplanar distributed force? Okay, so I again consider another coordinate system where my load is expressed omega or W, okay, and with respect to x. Okay, now since the width direction the pressure is not changing, so this two-dimension case, because pressure is the function of only x, so it is a coplanar problem. In this case we can reduce this into a one-dimensional problem. Okay, then what is this W? So it is distributed like this. W is varying with respect to only x. Okay, so P of x into B will be Newton per meter. So now this becomes, so W is Newton per meter. When we have a distributed force in a plane like this, okay, this is the W axis, this is the x axis. How this distributed force is changed into concentrated force? Okay, Now, for that, you take a small element. So at this point, it is W, the height is W, and this is this small length is dx, this x distance from this end. Okay, so then the small force dF, okay, dF is, this is W into dx. Why? W is Newton per meter or kilonewton per meter. This will have meter. So this gets cancelled. You'll get the concentrated force in Newton. So this is for the small element. If you are integrating dF, if you are integrating to get force, integrate dx 0 to L actually, right? So this is nothing but the small area. This is area. This is small area. Fine? Right. Now integration of this will give what does it mean? The force is nothing but the area of this distributed force. So the entire area where it is distributed, that is this area. So the force is area. Okay, force is area. Now that resultant force, where it will act. Okay, for that, right, say for example, it is the resultant force that is acting at a particular location, x bar, right? So x bar into F. I take moment about this axis. F into x bar is equal to this integral x is the distance, and omega dx is the small force. Okay, summation, integration of this will be equal to the resultant force. Okay, fine, or resultant moment. Now this we know dA. So x bar F is integral x dA. What is integral x dA? It is first moment of area. Fine. And what is this F? F is A. Already we have found out F is A. So now x bar equal to integral x dA. I'll write here. X bar equal to integral x dA by A. What is this? This first moment of area divided by the total area will give you the location of centroid. What do we understand? The force is nothing but the area, and the line of action of the force will pass through centroid. Then what is this point? This point is centroid point. You need to understand this. Okay? So the location of the force, the line of action of the force passing through is through the centroid. Okay? With that, we are going to now change or convert this redistributed force into a concentrated force. I am not going to completely solve this problem numerically with all values, but I am going to just give you the free body diagram. Once you understand the free body diagram, you can use the three equilibrium equations and you yourself can solve the problem. Now you see here, Okay, I have one varying load, another uniformly distributed, another linearly varying load. Okay, I divide this. First, let me take this. So I am drawing the beam. This is the beam, and you see this is hinge, and this is a roller. So this is pretty straightforward. So you will have, say if it is A, AY, AX. Okay, you take this B, this is C, this is D, this is E, and this is F. Okay, then E, you will have only 1. You already know these directions, I am assuming. Okay, and I am placing this. So this is an inclined force, so I will resolve into components. 20 cos 45, 20 sin 45. I have done with this. And this force, sorry, this couple, you can place as such. Okay, it is 10 kilonewton per meter. Now, how to convert these 3 distributed force into concentrated force? Okay, I'll just first take this. What we learned? We learned force is area. So area of this triangle, I am just drawing it here. The area is, this side it is 25. The height is the load. Okay, and this length is 2 meter. Right? So the area is of, it's a triangle, of into 2 into 25. So 2 gets cancelled, and 25 kilonewton is the force. The location of it, it will pass through the centroid. The line of action of the force, 25 kilonewton, will pass through the centroid. The location of centroid, from this end, it is 1/3 of the base. If you are coming from this end, it is 2/3 of the base. So I am able to get the distance as well. Right? So now, where I have to place, I am placing it here. 25 kilonewton, and the distance from here to here, this distance is, okay, 2/3 of 2. So 4/3 is this length. So when you are taking moment, the perpendicular distance is important. 2, 3.5, 4.5, 5.5 plus 4/3 is the distance if you are taking moment from this, about this end. Right? Now, so this is done. The location is known, the force is also known. Now we will come to this. And we will first see this force. You see this force, this area, I don't have a direct formula. So what I am doing, further I am reducing it. Right. So the 10 kilonewton per meter uniformly distributed force up to this. This could be seen like this. You can take the entire rectangle or you can, so the entire rectangle, the length is 3.5 meter, or you can take the rectangle like this also. This is 1.5, this is 2. You can take the entire rectangle as one area, then you know it will be passing through the mid because the centroid is at the mid for rectangle, then what is the height? It is 10. So then area is 10 into 3.5 is 35 kilonewton. So the 35 kilonewton force is acting this entire area and passing through the mid. Mid is 3.5. So this length is 3.5 by 2. Right? Otherwise, if you don't want to do that, you can first find the concentrated force for this. Then it is area is 10 into 1.5. So that will be 15 kilonewton, and here also 20 kilonewton. This way also you can solve. So I can place two forces here at the appropriate location, or the single force I can use it here. So if I am using only the single force, it will be approximately here 35 kilonewton, and the perpendicular distance is 3.5 by 2. Fine. Lastly, now we have this area. This is a triangle. Okay. I am drawing it here. What is the base length? 2 meter. Fine. What is this height now? Earlier it is 30. 10 already we have taken here. So this will be 20. This height will be 20. So 20 kilonewton per meter is taken. Right? Now area is half into base into height. So 20 kilonewton. 20 kilonewton force will be acting from this end, 1/3 of base. If you are coming from this end, it is 2/3 of the base. Right? So what we have essentially done? We have distributed forces acting on the bodies. Now how to deal with distributed force? So we have to first idealize that into a coplanar distributed force. Then the W force, Newton per meter, is acting either in the form of uniformly distributed or linearly varying, or like this also varying. That is also linearly varying only. Fine. Now when we have such distributed forces, how to change that into single point concentrated or point load, single point load. So for that we have used this. The magnitude is the area and the location is passing through centroid of the shape which we are considering. Okay. Now you see here is 20 kilonewton, where it will be acting? It will be acting 20 kilonewton, and this distance is 1/3 of 2 or 2 by 3. So all the distances are known, all the magnitudes are known. I have placed everything in the free body diagram. Now we can use 3 equilibrium equations to solve or to find out 3 unknowns, namely EY, AX and AY. I hope you are clear with this concept as well. Thank you.